What can we say about the properties of ionic bonds? And when I think of these, I'm typically thinking of salts, substances like sodium chloride, for example. The first thing that probably jumps out in your mind is that these things dissolve in water. These would make very bad building materials for a house, for example. What's really happening is that lattice is getting broken up by water molecules. It's dissociating in water. Remember, salts always involve a metal bonded to a nonmetal, left of the staircase to the right of the staircase. And we can show that dissociation as having that ionic bond being broken. And now in solution, you've got the sodium cation and the chloride anion. AQ means aqueous, dissolved in water. Water is not acting as a chemical participant. In fact, this entire process is considered a physical process. And this is the dissociation process. Another thing about salts is that they can form these incredibly nice, straight fracture lines. They're brittle. Although the bonds are quite strong, they are relatively brittle. One way that at least helps mechanically to understand this is to imagine a lattice of sodium chloride cations and anions. There's your cation, there's your anion. Now notice that we have lots of attractive forces, plus to minus, plus to minus. It's only the diagonals, the longer distances, that are repulsive. But if this got frame shifted, if this entire line got pushed over slightly, all those forces would suddenly become repulsive, and that could lead to a fracture line. This is the analogy used to explain why these ionic compounds can crack so easily and why they're not malleable. Okay, to name these things, we always start with the cation. We'd never call salt chloride sodium, table salt that is. We'd call it sodium chloride. So use that as a hint to always put the cation first. Write the charges as personal notes typically will help you see how many of each you need. That sounds unnecessary, but wait till we get to more complex examples and you'll see how you need to do that. And then either just switch those charges by saying, I'm going to put that one there and that one there. We call that drop and switch. Or just recognize that this is an uncharged ionic compound. Ionic compounds are always uncharged. So that's the quick way to come up with the ratio, 1 sodium for 1 chlorine. The reason we did that is because it's not the case with magnesium fluoride. Now, if you like to logic these out, you could simply say, I know that magnesium is a group 2 metal. It's going to lose 2 electrons. I know that fluoride is group 17. It's going to gain 1. Therefore, it's not going to work to have 1 of each. We're going to need 2 of those fluorines, 2 of those negative 1s to offset that positive 2. That's a mouthful. So start by recognizing this would be called magnesium fluoride. By the way, do notice that we do not use monodi and tri when naming these things. Unfortunate, but true. We just say magnesium fluoride and figure it out. One quick way to figure out the ratio of them is to use the drop and switch method. Write the charges above, 2 and 1. I usually recommend people do the absolute value because all too often I see a -1 right there, which is annoying. And in fact, the 1 at all isn't even important. 1 is implied if all you see is just magnesium. And then just switch them over and you get MgF2. I hope that's clear. This is the properties of ionic bonds.